I thought I would show you some material that we've been studying in probability theory. Probability theory is an applied mathematics course, but I was recommended to take it by my advisor, my graduate student advisor, not my doctoral advisor, because he said that the instructor for it was really, really good, and then I might like it because I'm studying analysis, and the two topics are very, very similar. So I listened to him and I took it, and I'm glad I did because the instructor is probably the best one at the university. I don't know about the whole university, but definitely the math department. Not as a dig to anyone in particular, just when I went to my analysis instructor and I asked him, should I take this probability course? The first thing he said to me was, who's teaching it? And I said his name, and he says, then you should definitely take it because he's the best. So I got a ringing endorsement from my analysis instructor. So I took it, and I'm glad I did. And so the reason I'm talking about probability now is because I have a test on Tuesday, and I thought I would do two things. I would tell you the way I study for these graduate exams, and then I'm going to show you my favorite theorem from real analysis, and I'll show you why the two are related. So this packet of notes he gives us, and it's pretty good, but this particular packet is not what we're going to be tested over. That was from last semester, but it is part of the chapter 5 notes that he gave us. But this chapter of notes he gave us, it's from his own personal notes, but it looks like he's writing a book here. So you can see this whole packet here is about, it says limit theorems and probability, but this is really just the first section, which is about the central limit theorem and the Berry-Yassine bound. And he goes through the proofs of all of them, and it gets pretty intense in spots. Like the Lindeberg central limit theorem takes like 2 pages worth to prove. He says we're going to need to know the theorem, but not know how to prove it, because that's too much. He might ask us to prove the Lyapunov central limit theorem, but maybe not. I'm going to do it anyway, though. And then obviously he wants us to know the definitions, and he wants us to be able to apply the material that shows up in this packet. So it's really just this packet. I have 3 packets here. But this one I keep with it because it's chapter 5. This one is chapter 6, but he says it's not going to be on the test, so it's really just everything in here. So what I typically do is that I will go to this part here where he talks about asymptotic negligibility, and he says we need to know the definition. So really all I do is I look at that definition, which is this limit and then supremum probability bigger than epsilon equals 0 for arbitrary epsilon. So what I'll do is I will basically write that thing down 10 times until I can do it with my eyes closed and don't even have to think about it. I know I'm kind of turning my brain off at some points, but I think the strategy that seemed to work for me, like, I'll teach my hand because my hand will learn faster than my brain. And then eventually, it'll become natural for your hand that eventually your brain will just make the connections, I think. I don't know how your brain works, but my brain kind of works that way. Just do something by hand over and over and over and over and over and over and over until eventually you learn it. Because, again, you don't learn to play the guitar by watching other people play or by studying the notes. You pick up the guitar and just beat on it until music comes out, until eventually you start to see what's really going on. And I do think the same is true for mathematics a lot of the times. Seeing examples is invaluable, and then trying to deconstruct those examples and make up your own is even better. But baby steps. Don't bite off more than you can chew. So that is probability theory. That's kind of how I study, just break things apart, write down the theorems and whatnot. So my favorite theorem in analysis is actually a theorem from probability theory, but the two are so closely related that you could mistake it for a theorem in measure theory. So this is actual probability. This was me doing the homework last night, just trying to make heads or tails of it. I know it doesn't really mean much out of context, but it's what it looks like. So why is this theorem my favorite? So my favorite theorem in real analysis has a name. It's called the Borel-Cantelli lemma. And I know technically it's a lemma, so it's not like a theorem. But lemmas are just tiny theorems that help prove a bigger theorem. And there's a reason why this one's my favorite. So there's a tiny story, which I'll tell quickly. When I took measure theory twice and then basically took it a third time this semester, there were a number of theorems that showed up that I had to memorize for my qualifying exam that I just couldn't get into my thick skull. And one of them was Egorov's theorem. Egorov's theorem is about having a set of some finite measure, and you have pointwise convergence of functions, and then you can find a closed subset of it, of arbitrarily, such that the difference between that set and the original set is very small. You can make it as small as you want. And the convergence on that set is uniform, which is nice because if you have a uniform convergent sequence of functions, particularly if they're continuous, for example, then you know the limiting function has to be continuous. So that's in a roundabout way of what Egorov's theorem says. And I read through the proof of it several times and wrote it down and tried to, just memorize it and learn it and figure it out. But it just wasn't sticking with me. And I couldn't figure out why. Just some proofs were more natural for me, and Egorov's was not one of them. And I also remember the name, right? Egorov is a name I don't really forget. So it's a theorem that I think about on and off. Like I know the name, I know the statement, yet the proof of it is just I couldn't get around. So how does this fit with Borel-Cantelli lemma? Well, last semester I took probability 1, and I remember thinking that this was a lot like measure theory. There wasn't really much difference between it and a low-level measure theory course. And one of the first lemmas that we came across was this one, the Borel-Cantelli lemma. And my instructor said that he was going to make one of us go up to the board and prove it. And I decided to volunteer rather than just have him pick someone. So I volunteered, and he goes, okay, you can do it. So on that next week, I went up to the board and I proved the Borel-Cantelli lemma. And the way I learned the lemma is I just looked at his notes that he gave us, so notes like that, and I just wrote it down a bunch of times. I think I wrote it down like 20 times until eventually it became supernatural, and I understood it, and it became a part of me. Why is that important? Is because one day I was looking at a proof of Egorov's theorem, and I saw the Borel-Cantelli lemma in it. A bunch of proofs I read never had Borel-Cantelli lemma mentioned until eventually, this became, a part of my analysis thought process, like the way that it's proved. And then it basically was the switch that I needed to learn how to prove Egorov's theorem. So for that reason, this theorem is kind of special to me. Plus, I did it up at the board. It's also a very simple lemma. It's not very complicated. So I have personal attachment to it. So what does it say? So the statement is, hopefully I remember how to do it. Otherwise, this is going to be really embarrassing. But you have a finite measure space. Finite measure space. So X is the space that we measure on, mu is our measure, and sigma is the set of all measurable functions. Or the set of all measurable sets, not functions. So that's our presupposition. And what it says here is that if the sum, well, hold on. if we have a family, I need to start here. If I have a family of measurable sets such that the sum of the measures of each individual set converges. So you add up all the measures of all the sets inside of this little family here. And if they sum to a finite number, then you can say the following. The measure of the limit superior of En as n tends toward infinity is equal to 0. So that's the statement. And I will prove it here, hopefully, in the next few minutes. It's a very short proof, which is why I like it. Well, okay, I have many reasons why I like it. The short proofs I like the most. So the first thing I do when I look at this and say, okay, what do I start with? Well, the first thing I always start with is I just write down everything I know. So, originally I would just write this. I'm not going to, and then I would write this. So the big question is what's happening here at lim sup. So it's important to remember what the definition is, otherwise you're kind of stuck. Definitions are important. So what does lim sup En mean? If you're like me, you have trouble remembering it versus like what lim inf is. And here's the way I keep them straight. The m in lim looks like the intersection. And then the u in sup looks like the union. So I have intersection, union. And then I put my E sub k. And k is at least n. And that n runs from 1 to infinity. So that's the definition of lim sup. Then what do I know? Well, if I call an the union k greater than equal to n of ek, really I'm looking at this piece here. If I call that an, these sets, this collection of sets, is descending, which means that A1 contains A2, which contains A3, contains blah, 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 so on and so forth. And so what this means is, because this is a descending sequence of sets, and I'm on a finite measure space, I'm allowed to say the following. I can say that the measure of the intersection of n equal 1 to infinity is equal to the limit of the measure of an as n tends toward infinity. Let me double check that to make sure I didn't make a mistake, because I am doing this from memory. You'll find that when you're in a type of program like this, that most of the time you're going to make a lot of bad mistakes. Mistakes are kind of the normal. But the most important thing is that you correct those mistakes and you get the right answer in the end. So don't feel too bad if you make a lot of mistakes. Just make sure that you finish, you correct the mistakes. So that's what we can say. And now, once I make all of these observations, I'm pretty much done. I just need to put it all together. So we'll write this. 0 is less than or equal to the measure of lim sup en. This just comes from the definition of measure. Measure can never be negative. Measure is always a non-negative function. So it's at least 0. Now I'm going to apply the definition. So I have intersection n equal 1 to infinity, union k k bigger than or equal to n e k. And now I'm going to use my substitution here. I don't really have to do this step. It's just I like to break it down so that's easier to follow. So I have the intersection of ANs. But then I can use this property. This property, by the way, is called the continuity of measure. So this means that this part here is equal to the limit of the measure of n tending toward infinity. But what does n equal to? So now I'm kind of, this is the reason why I said that it's not necessary to do this notation with an. I was just illustrating a point. Because now I'm going to write measure of the union k greater than n e k. But because mu is a measure, we know that we can apply countable subadditivity here. That's the third property of measure. Typically, it's presented as the third property. So this becomes the limit, as n tends toward infinity, of the sum of measures of e k, where k is equal to what? At least n, right? So it's at least n and it goes up to infinity. But now you take a moment to look at this statement. N is tending toward infinity. This sum runs from n to infinity. So this sum can only get smaller for the larger n's that you pick. But what do you know about this sum? You know that it converges. That's this property up here that we have yet to use. So since this converges, you know that these measures have to get smaller and smaller and smaller. And you add fewer and fewer and fewer of them together. So this sum has to tend towards 0. Otherwise, it wouldn't converge. The limit of this sum tends to 0. Otherwise, it wouldn't converge. And so look at what we've shown. We've shown that 0 is less than or equal to the measure of lim sup en. And that is equal to 0 on the other side. I probably could have thrown in a less than equal to, but I don't think anything here was inappropriate. Oh, actually, no, I'm lying. I'm definitely lying. I forgot something. Countable subadditivity means that this is less than or equal to. Okay, I knew something was up. So, but it's still, our result still holds. 0 less than or equal to the thing that we want, less than or equal to the thing that we want, which is 0. So I've sandwiched it between 0 and 0, so it has to be 0 at the end. And that's the Borel-Cantelli lemma. And the reason it is a lemma instead of a theorem is because it's used to prove bigger things. Like Egorov's, for example. It's a stepping stone. So I hope you found this interesting. I hope you appreciate this lemma as much as I do. And as always, thank you for watching.